Everyone, today we have Richard Wong speaking on Picard groups of stable module categories.
Okay, cool. Thanks everyone for coming, and thanks to Sarah for organizing this. I think it's great that technology allows us to stay connected in these times. And I think it's also important to try and explore how we can use it to be more inclusive and equitable. So I'm going to post a link to my slides in the chat. So feel free to use those if I go too fast or go too slow. And of course, feel free to stop and ask me any questions you have as well. Okay, so today I'm going to be telling everyone about Picard groups of stable module categories. The first thing I'm going to do is I'm going to tell you about what stable module categories are. And then I'm going to tell you what Picard groups are. And then I'm going to talk about computational tools that we have to compute said Picard groups. So we'll start with the stable module category. And what this is this exists in the setting of modular representation theory. And what that is it's representation theory of finite groups such that the characteristic of the field divides the order of the group. So in representation theory, you're interested in studying like modules over the group ring. And the thing that is interesting about this representation theory is that Moshka's theorem does not hold. And what Moshka's theorem says is that the group ring is semi-simple if and only if the characteristic does not divide the order of the group. And the proof of this involves, well, to prove Moshka's theorem, you divide by the order of the group, which you can't do in this case. But the more important corollary of this example is that it turns out that not every KG module is going to be projective if Moshka's theorem does not hold. And so one thing you might ask is, what happens if you quotient out, if you kill off all of the projective modules? And the answer to that question is you obtain the stable module category. So this category has objects, KG modules, and the morphisms in this category are given by the R module morphisms, but now you're quotienting out by the homomorphisms that factor through a projective module. So in this way, you're quotienting off or killing off or localizing away these projective modules. And in the stable module category, you have the notion of stable equivalence. So we say two maps are stably equivalent if their difference, f minus g, factors through a projective module. And you can check to see that this turns out to be an equivalence relation. And now that we have this new kind of equivalence relation, you might think maybe the stable module category is coming from some kind of homotopy category. Or you can like look at this notion of equivalence, and it turns out that you would be right. The stable module category is the homotopy category of a stable model category structure on KG. And what a model category structure is a way to encode some kind of homotopy theory into the structure of a category. And stable means it's there's a notion of suspension, just like there is in spectra. That's it. So the suspension functor is an equivalence. So the data that defines a model category structure, to tell you what that is, I need to tell you the weak equivalences and what the fibrations are, or equivalently the cofibrations. So the weak equivalences are going to be the stable equivalences. So F is weakly equivalent to G if F minus G factors through a projective. And the fibrations are the surjections. And you should think of this as projective replacement or cofibrate replacement. And the acyclic fibrations, so the maps that are both fibrations and weak equivalences, are the surjections, are the maps that are surjections with projective kernel. So these two things tell you what the model category structure is on KG modules. And of course, to be a stable model category, you also need a notion of suspension. And in the category of KG modules, we define the suspension as follows. You take an inclusion into an injective module, and then you define the suspension to be the cofiber of this injection. And you can check to see that this becomes this satisfies the properties of a suspension functor in your model category structure. There's also a notion of tensor products in KG modules. You can tensor over your field K, and this also gives you a symmetric monoidal structure on KG modules. And so in the stable module category. So this model categories are kind of a classical way to describe homotopy theory. And you can also boost this up to an infinity categorical statement. So it turns out the stable module category is also a stable symmetric monoidal infinity category. So infinity categories are just another way to model homotopical structure in a nice way. So this is kind of what the stable module category is. And now I'm going to tell you about a different way to think about it, which is maybe the way that I think about the stable module category. So from now on, instead of a group whose order is divided by the characteristic of the field, we're just going to restrict our attention to the setting where G is a finite P group. And the reason that we do this is so that we have the following theorem due to Akil-Matthew, which says there's an equivalence of symmetric monoidal infinity categories, even stable ones, between the stable module category and the category of modules over the G Tate fixed points. Of K, consider it as like an Eilenberg-MacLean ring spectrum. So I'm going to tell you what KTG is in a little bit. It turns out to be an E infinity ring spectrum. But I'll talk about that on the next slide. To give you an idea of how this theorem is proved, you go through some identifications. So this functors from BG to perf K. What this is the category of perfect, so compact K modules with a G action. So morally speaking, this is modules over K with a G action. And if you complete this, incomplete this, this turns out to be equivalent to modules over the G homotopy fixed points. of K with a trivial action. So you might see how this is related to the stable module category. And it turns out if you localize away from this algebra, the G dual of K, this localization is the same as killing off the projective modules. And that's how you get this result. And it turns out this localization is the same thing as the Tate construction. So that's how you get this result of Achilles. So now, as promised, I'm going to tell you what homotopy fixed points are and what Tate fixed points are. So the KHG is the homotopy fixed points of K with a trivial action of G. And it's also equivalently the E-infinity ring of cochains on BG with coefficients in K. And the thing that is nice about this is that we already understand its homotopy groups very well. There's an isomorphism of graded rings between the homotopy groups of the homotopy fixed points, identified with negative degrees of group cohomology. With trivial action and coefficients in K. So for example, if P is the prime 2, then the homotopy groups of the Z mod 2 to the n homotopy fixed points, again with a trivial action, is just a polynomial ring in degree -1. Should be a -1. And for P odd, so for a cyclic, for an elementary abelian group of rank n, then the group cohomology is a polynomial algebra tensored with this exterior algebra. So we're already familiar with the homotopy groups because we know a lot of things and a lot of ways to calculate group cohomology. Moreover, so that's one way to calculate the homotopy groups of the homotopy fixed points. But we also have the homotopy fixed point spectral sequence. So a spectral sequence is some kind of algebraic machine that if you have a ring spectrum R with a G action, if you understand the homotopy groups of R and you understand how G acts on these homotopy groups, so if you can calculate this group cohomology, then you can use this spectral sequence to compute the homotopy groups of the homotopy fixed points. So this is really good for us because this allows us to do calculations.
Sorry, can I ask a quick question?
Yeah, go ahead.
Are you assuming here that R has finite homotopy groups? Or why?
Yeah, there's like some niceness conditions on this, I think. Well, even for any of the examples we're considering today, that'll be true.
Okay, thanks.
Right. So dual to the notion of homotopy fixed points, there's also a notion of homotopy orbits. So instead of taking the fixed points, you take the orbits of this G action. And you also have a homotopy orbit spectral sequence. So the E2 page of this is the group homology on the homotopy groups of your ring R. And it converges to the homotopy groups of the orbits. And now this is homological instead of cohomological. And you also have this isomorphism between the homotopy groups of the orbits and the group homology. By the way, you can see how this might be true just by looking at the spectral sequence, because for K and Eilenberg-MacLane spectrum, it's just concentrated in 1 degree. So you can see how you get these isomorphisms out of the spectral sequence. Okay, so now that I've talked about orbits and fixed points, so just as there is a norm map in group cohomology going from the orbits to the fixed points, by sending an element A in here to the sum of G acting on A, G and G. And of course, the fixed points are going to be H0 of the homology, and this is H upper 0 of cohomology. So there's a norm map going between these two groups, and in a similar way, you can construct a norm map going from the homotopy orbits to the homotopy fixed points. And just as you can stitch together group homology and group cohomology via the norm map to form Tate cohomology, so to compute, you would take a projective resolution, mapping down to your thing K. And you can also compute using an injective resolution. And you can stitch these things together with the norm map. So this gives you a complete resolution. And the homology of this chain complex gives you Tate cohomology. And you have isomorphisms with group cohomology in positive degrees and group homology in negative degrees. And you have these co-kernels and kernels from the stitching together. So you can stitch things together in cohomology and in Tate cohomology. And you can also do a similar thing by taking the Tate fixed points to be the cofiber of the norm map. So this here is a cofiber sequence. And of course, we had spectral sequences to compute the homotopy groups of the homotopy orbits and the homotopy fixed points. And so, of course, one might expect, and we do get, a Tate spectral sequence whose input is now Tate cohomology, and whose output is the homotopy groups of the Tate fixed points. Now, a warning, Tate cohomology is a little bit weird. It turns out that multiplication in negative degrees is going to be, in the Tate fixed points, is going to be the same as multiplication in the homotopy fixed points, because we have, for example, maps from the homotopy fixed points to the Tate fixed points, and we also get a morphism of spectral sequences from the cohomology And so you can kind of imagine how multiplication in negative degrees, where these two things agree, is going to be the same. However, multiplication by elements in positive degrees is more complicated. So for example, if G is an elementary abelian group of rank n bigger than 2, so if G is isomorphic to Z mod P to the n, it turns out that multiplication by any elements, any two elements in positive degree, is always going to be 0. So this is kind of a weird thing. It's hard to write down the multiplication, but you can see where it's coming from through maybe this Greenlee's spectral sequence or Czech spectral sequence. And you can kind of see how the multiplication comes from this. Right, so to remind you why we are talking about these homotopy fixed points and fixed points, we go back to this theorem of Akil, which says there is an equivalence between the stable module category and modules of the Tate fixed points. So this is why we care, or one reason that we care about these things. And this is also conceptually very satisfying, because historically the study of the stable module category was really informed by what we knew about group cohomology and Tate cohomology.
Can I ask a question at this moment? Sorry, how important here what you consider it finite P group here?
Yeah, I didn't explain why, and that's a great question. The reason that we restrict to finite P groups is so that the module, or sorry, we want this to be, I think the term is unipotent. So we want the modules to be generated as the localizing subcategory of the unit.
So it's related somehow to equivalent results on cohomology of
right.
group in terms of elementary subgroups.
Yeah, and yeah, you can use like restriction to obtain results about general P, groups in general characteristic by restricting to P groups.
Okay.
So this is just for simplicity.
Okay.
Any other questions while we take a break?
Hi, Richard.
Yeah.
How are you doing? I was just wondering whether there might be some relation to like the Hopkins-Kuhn-Ravenel stuff with like focusing on P groups.
I actually don't know very much about Hill-Hopkins-Ravenel or why they focus on P groups.
Or like in Hopkins-Kuhn-Ravenel, like they focus on like the cohomology of B cyclic group or BP group. Because maybe let's talk afterwards. But yeah.
Okay. Yeah. I think they also use like homotopy fixed points and Tate fixed points to do calculations.
Yeah.
I mean, just because of how the groups are acting. I don't know if there's a relation to the stable module category.
Mm-hmm.
Okay, so that was the stable module category. Now let's talk about Picard groups really quickly. If you haven't seen me give this talk before, Picard groups are, you can define the Picard group for any category C with the appropriate notion of something like a tensor product. And you need the unit for that tensor product as well. And so the Picard group is this group which is, the elements are isomorphism classes of invertible objects, And the multiplication is given by taking the class of the tensor product. And the dual is going to be taking the class, sorry, the inverse is going to be taking the class of the dual. So this is an interesting thing to compute that gives you information about your symmetric monoidal category.
Sorry, what do you mean that, like, the Hom, like, right? Isn't that just a set? The Homs?
So I guess maybe your category is enriched over something that makes sense. Yeah.
Okay.
Yeah. So in particular, all of these elements in the Picard groups are dualizable.
Okay, so you just have a tensor Hom.
So yeah, this is a tensor Hom, the tensor homojunction thing.
Thanks.
Yeah, so the Picard group is this thing. And some examples of categories that you might want to compute Picard groups are. So if you have a stable symmetric monoidal infinity category, you get some additional structure in your Picard group because suspension should play nicely with tensor product. So examples are the category of spectra, the derived category of a commutative ring, modules over an E-infinity ring spectrum, and the stable module category. So you can think of this as some kind of generalization of modules over a ring, because we saw that for P groups, we have this isomorphism. So some examples of Picard groups. For the category of spectra, it turns out that the Picard group is the integers. And what that means is for any invertible spectrum, it's going to turn out to be equivalent to some suspension of the sphere spectrum, some suspension of the unit. And the theorem that I'm going to sketch the proof of was originally due to Dade. And he computed the Picard group of the stable module category for E and elementary abelian, so Z mod P to the N P group. And he showed that it was cyclic as well. So Dade used representation theory in his proof, and Akil Matthew came up with a proof using Galois descent.
Sorry, I have a question. You
Yeah.
you said elementary abelian, but you wrote abelian. Does it hold for Z mod Pn, for instance?
Yes. It turns out that the homotopy groups are going to be the same, so you can do similar things. I think that's right. I guess to answer the question, yes, but I think you can really just reduce down to elementary abelian groups.
Okay. Okay, thanks.
Is there any complex oriented descent happening? Like where, sorry, I know what's there, and maybe I'll ask you later about this. Sorry.
Yeah, I'll tell you kind of how things go, and then you can ask that question then.
Yeah.
Right, so Galois descent, which is using Galois extensions of ring spectra and the homotopy fixed point spectral sequence, is what I mean by this. And it's a little bit weird because it's reverse Galois descent, but I'll talk about what that means when we get And really quickly, you can do better than the Picard group. You can, in fact, get the Picard spectrum. So instead of just looking at isomorphism classes of objects and throwing away all higher data, you can actually just choose to keep track of that. And you get a Picard space, or the infinity groupoid of invertible objects by keeping track of this higher data. And this turns out to be group-like E infinity. And so equivalently, we obtain the connective Picard spectrum. And the nice thing about this is that this functor commutes with limits. So this is really good for descent calculations. To say a little bit about the Picard spectrum for E infinity rings. So the Picard spectrum for R is the Picard spectrum for the category of modules over this ring spectrum. So in pi 0, you recover the usual Picard group. And in higher degrees, it turns out that this Picard spectrum in degrees higher than or equal to 1 is equivalent to the suspension of GL1 of R. So the units of this ring spectrum. So this is really nice because we understand GL1R very well. And so we know it's zeroth homotopy group. And we have this isomorphism between homotopy groups of GL1R and the homotopy groups of R in degrees bigger than or equal to 1. One thing I should note is that this is just an equivalence on the level of groups, and the ring structure is going to be radically different. So that's Picard groups. Are there any other questions while we take our second break?
Sorry, what do you mean by ring structure on the Picard spectrum?
Sorry, I meant, so GL1R is also infinite. That's what I meant.
So, yeah, I see. Yeah, you mean only about GL1?
Yeah, sorry, I was talking about GL1R.
Okay, yeah. Thanks.
Okay, so now that we have Picard groups and the stable module category talked about, we can now move on to computational tools. So namely the homotopy fixed point spectral sequence. So the reason to motivate why we would consider Galois extensions of ring spectra is that if we have a Galois extension that's also faithful, then we get this equivalence of categories between R modules and S modules with this induced G action, and you take the homotopy fixed points. So if we have a faithful Galois extension of ring spectra, if we apply pick to these things, we get an equivalence pick R to pick of this thing. And the nice thing about pick is that it commutes with limits. And so we get that this is equivalent to the positive part of Picard group of S HG. So what this is telling us is that if we can compute the homotopy groups of the G homotopy fixed points on pick S, then we can recover the Picard groups of R. And since we have this equivalence, we have this homotopy fixed point spectral sequence. And the thing that we're interested in computing is going to be pi 0 of pic s of hg, which we saw is going to be equivalent to the Picard group user groups, or the Picard group of R. So now that we have the motivation done, I'm going to tell you what a G-Galois extension is. So you say a map of E-infinity ring spectra is a Galois extension if first the induced map between R and the homotopy fixed points of S is an equivalence. And secondly, if this, if you look at S tensor S over R, if this is equivalent to the G dual of S, then these two things give you a Galois extension of ring spectra. And moreover, you say that a Galois extension is faithful if the following property, if S is faithful as an R module. So that means that if you have an R module such that S tensor M over R is contractible, then M itself is contractible. And if you have a faithful G-Galois extension, then you can do descent. So our first example, and really the main example of this talk, is going to be between from real K theory to complex K theory. This is a faithful Z mod 2 Galois extension of ring spectra. And this is nice because ultimately we want to compute the Picard group of KO. And the nice thing is that we understand the Picard group of KU well, and we understand how Z mod 2 is going to act on this. So the nice thing about KU is that it's, two periodic with a generator in degree 2, and it's homologically very simple. And on the other hand, the homotopy groups of real K theory is more complicated. It has the bot song Z2, Z2, 0, Z, 0, 0, 0, Z. And it's eightfold periodic. So I won't prove that it's a Galois extension, but what I will prove, I'll give some evidence for why it is Galois. But what I will prove is the fact that it's faithful. So how do you check faithfulness of ring spectra? Well, the proposition due to Reminisce, who, by the way, came up with the idea of a Galois extension of ring spectra, is you have, it's faithful if and only if the Tate construction is contractible. And this is a much nicer thing to check because we can calculate using the Tate spectral sequence. Okay, so let's do some computations now. So this picture is a picture of the Z mod 2 homotopy fixed point spectral sequence. And what we're doing right now is we're computing the homotopy groups of the Z mod 2 homotopy fixed points of KU. And to compute the E2 page, we need to understand the group cohomology of Z mod 2 with coefficients in Z. well, so remember that pi t of ku is z with a generator in degree 2. And it turns out that when z mod 2 acts on this, it acts trivially for t equals 0 mod 4. And for t equals 2 mod 4, then it acts by conjugation. So we need to do these group cohomology calculations. And so for 0 mod 4, you get what happens in this line. Sorry, this line. So you have a z in degree 0, and then z mod 2's in even degrees after that. And it's periodic, so we get lines that look like this. And for z mod 2 with the conjugation action, you just get z mod 2's in odd degrees. And that's what these blue lines are. So that's what the E2 page looks like. And you need to do some kind of geometric argument to understand the differentials. And it turns out there's only the D3 differential is the only non-trivial one. And moreover, the homotopy fixed point spectral sequence is multiplicative. So once you compute, for example, this red D3 differential, then it propagates through the rest of the spectral sequence. So the E infinity page, what's left over, looks like this. And this is the E infinity page. And now you can see why Ku HC12 is equivalent to Ko, because now you see this eightfold periodicity. So Z, Z2, Z2, 0, Z, 0, 0, 0, Z, and it repeats. So why did I calculate the homotopy fixed point spectral sequence first? It's because this maps into the Tate spectral sequence. And so we can import differentials and import classes, which will give us enough information to compute the Tate fixed points. So this is a picture of what the E2 page looks like. And everything above the 0 line so all these classes and differentials, sorry, everything above the 1 line. All of these things are coming from the homotopy fixed point spectral sequence. And everything below, you can calculate Tate cohomology of Z mod 2, Z, and Tate cohomology. So this is the trivial action, and this is the conjugation action. And you just get Z mod 2's in either appropriately odd or even or odd degree. So that's how you get the E2 page of the spectral sequence. And moreover, the Tate spectral sequence is also multiplicative. And so importing this D3 allows us to import and then propagate all of these other Z3s, D3s. And so these are all non-trivial, and everything is either hit or is hit by a D3. And so this tells us that the E infinity page is the trivial. There's nothing left, which shows that the Tate fixed points is contractible. So that's good. And what's even better is that not only do these computations allow us to show that it's a Galois extension of ring spectra, it also helps us in computing the Picard group through Galois descent. So recall the spectral sequence due to Matthew and Stoyanowska has E2 page that looks like this and computes the Picard group's homotopy fixed points. And the nice thing that Akhil and Vesna proved is that we have a comparison tool. And what this tool says is that if t minus s is bigger than 0 and s is bigger than 0, then we have an equality of differentials between the Picard spectral sequence and the usual spectral sequence. So this t minus s bigger than 0 and s bigger than 0 is coming from the identification between the homotopy groups of Picard groups and the homotopy groups of R for star bigger than or equal to 1. And this is coming from the construction of the Picard spectrum. But more importantly, they also show that this equality holds whenever the Rth differential is between 2 and t minus 1. And this is coming from kind of an identification in the stable range of a truncated spectrum. Sorry, this is n plus 1 to 2n of the Picard spectrum of R is equivalent to the nth to the 2n minus 1th truncation of R. Sorry, these are s's. So they have a more sophisticated comparison between the Picard spectrum and the ring spectrum. And this allows us to import quite a lot of differentials and helps us tremendously in calculations. So to compute the Picard group of KO, we're going to use the homotopy fixed point spectral sequence. So the first thing that we need to do is we need to figure out the homotopy groups of the Picard group of KU. And so we need to figure out what happens in pi 0 of pic KU, which is the Picard group of KU. And since KU is, the homotopy groups are really nice, and KU is even periodic with regular Noetherian pi 0, this tells us that KU, or pic of KU, is algebraic. So what this means is that the Picard group of KU is the same as the Picard group of the homotopy groups of KU, which is Z mod 2. And we can, now that we know that, we also know what, sorry, this is pic of KU. We can also compute the higher homotopy groups by computing the units of pi0 of Ku. And we know that this is either Z or 0. So now we can look at the homotopy fixed point spectral sequence. And what we need are the comparison tools. So we have for t minus s bigger than 0 and s bigger than 0, we can import everything in here. And we can import the E2 classes as long as 2 is bigger than or equal to t minus 1. So this is for r equals 2. So for t bigger than 3, and that's everything in this range. So that's the classes that we can import. And we can also import the D3 differentials for t minus 1 bigger than 3. So for t bigger than or 4, we can import the D3 differentials. Now this is getting kind of messy, but we can import any D3s that fall in this orange range. So now that we've done all this importing, we see that for anything above this line, so we're interested in computing pi0 of pic of Ku H Z mod 2. So we're interested in computing this. Now this is really too many colors, but this white line. And for everything above this line, we see that everything is either hit or going to be hit by a D3 differential. So the only things that remain in the 0 line are these 3 classes. So what this tells us is that the Picard group of KO, the size of it is at most 8, but we also know that KO is 8-fold periodic. So that tells us that the Picard group of KO is actually, the size is actually 8, and since it's 8-fold periodic, this is actually a cyclic group of order 8. So you can also prove this without using Bott periodicity, and this is covered in Gepner and Lawson's paper on Brouwer groups. I'm almost like way over time. So really quickly, another example of Galois extensions of ring spectra are for Tate fixed points. And if you have a normal subgroup of your finite P group, then this is a G mod H Galois extension of ring spectra. And this is good for us because we want to compute modules over the G Tate fixed points. However, these extensions are usually not faithful, but the work in progress that I'm doing, it turns out that this extension of ring spectra coming from Z mod 2, including into BQ8, this gives us this extension of ring spectra, and it's almost faithful. So it's faithful enough that you can do some kind of descent calculation. And I guess I'll end by saying, I guess, so explaining why this is a G mod H Galois extension of ring spectra. And the reason this is because we get this fiber sequence, and this tells us that this exhibits AG as the homotopy orbits of G mod H. So when you apply cochains, this tells you that KTG is the same as KTH HGH, or H here. But to show this tensor product part is a bit more complicated. You need the collapse of an Eilenberg-Moore spectral sequence, which computes the mod P cohomology of a fiber product BH tensored over BT BH. Which you can show is isomorphic to the above. So I guess I'll stop there, and thanks everyone for listening.
On behalf of everyone, I'd like to thank Richard. Are there questions?
Yeah, I have a question. So is there a map from the Picard variety to the algebraic K-theory of the Picard spectrum to the algebraic K-theory spectrum?
So this is true in, like, there's a map from K0, the group completion, to the Picard group. I'm not sure if this extends to a map between the spectra. I'm not sure.
Okay, thanks.
Hi, Richard. So I was just wondering about like that condition that you had about for a map of spectra to be a Galois extension, and you had this condition about that like the Tate construction should be contractible.
Yeah, that's faithfulness.
Oh, for faithfulness. So like, what does this mean for just for ordinary? What does this mean for a Galois extension of fields? Are Galois extensions of fields automatically faithful, or like is there like some take cohomology calculation you can do?
Yeah. So for Galois extensions of rings and fields, like if you take their Eilenberg-MacLane spectrum. Yeah. So for discrete rings and fields, it's always going to be faithful.
Oh, okay.
And
is there any intuition for this term faithful, or?
Yeah, because that it's like meaning that your target S is a faithful R module. So it like detects zero objects or contractible things.
Okay. Thanks.
So can I ask too? So like at the end you say some words like almost faithful. This words has some exact meaning, or it's like some intuition?
Oh, does it? I didn't mean it in whatever meaning it has. I meant that right here. So this Galois extension, the homotopy, the Tate construction. So KT mod 2. The group that's acting on this is Q8 mod Z mod 2.
Yep.
which is z mod 2 squared.
Sure.
And what I mean is that the Tate construction of z mod 2 squared, this thing is not contractible, but it's pretty close to being contractible. There's like some periodicity going on. So you can, or I hope, work in progress says that there's enough, it's close enough to being faithful that you can do Galois descent.
I see. So it's possible to have to know some differentials like in.
Exactly.
Mm-hmm.
Exactly.
Thanks.
Any other questions for the recording? All right, well, if not, I'd like to thank Richard again